Okay, so now after all these lemmas, it's about time for a proper result. So here is theorem 10. And we start just like in the previous lemmas. And now we want to apply a projection method. So we need sequence of projectors on X, and we take the same sequence on the other X because it's the same. And moreover, we expect them to be orthogonal projections. And of course, let's not forget that Pn should converge strongly to the identity. And the theorem says that under these conditions, the method Pn is an applicable projection method to A. Because Pn are orthogonal projections, this here is a Galerkin method. And as we learned earlier, on the level of coordinate vectors, it's just the finite section method. So we could just call this the FSM if you want, or we could just leave it as it is. So let's prove theorem 10. So let's start by introducing the little c as we did in lemma 9. And now remember Polsky's theorem. So for applicability of this method here, we need to show stability, and we also need invertibility of A. Okay, for stability we need invertibility of Pn, of course on the little subspace Xn for sufficiently large n. So let's start with a little n in the natural numbers. Okay, now introduce our subspace Xn as the image of Pn, and now start with a vector in that subspace so that we can apply our projected operators on it. And now the aim is to show that the positive definiteness of A is carried over to these projected operators here. So let's look at similar scalar products here, but now with Pn in place of A. Note that we're using Xn here, which was chosen from our subspaces capital Xn. And now if we want to use properties of A, we have to get that Pn here out of the way. Well, why not get it over here as Pn star? Now for orthogonal projections, Pn star equals Pn, so we can remove the star. And then of course you can ignore the Pn in front of the Xn, because Xn is already in the projected space, so in the subspace where Pn is projecting onto. So if you project again, then you stay where you are. So you can drop this Pn, and for the same reason you can drop that Pn. Okay, and now we can use positive definiteness of A. Okay, and if you read the whole line, then this already says that Pn is positive definite, and you can use the same constant little c here. And then just like in lemma 9b, we could conclude that this is an invertible operator on its little subspace. But here, I mean, we could essentially repeat part of the argument, which was Cauchy-Schwarz inequality, noting that this expression is always real and non-negative, so we can just assume we have modulus signs here. Okay, and now we divide by norm of Xn, which is here, but also here, and which leaves us with the following inequality, showing that Pn as an operator from Xn to Xn is bounded from below, so it is injective and has a closed image. But all the same is true for the adjoint, because A and Pn are self-adjoint, which makes this product here self-adjoint. So like in lemma 9, we can conclude that this is an invertible operator. And for stability, we still need boundedness of the inverses of these operators. Well, how do we get this? We get it from here, from the fact that they are bounded from below by the same constant c that does not depend on little n, only on a. It's not difficult to understand. Maybe it helps to draw this little diagram here. So the norm of the output is greater than or equal to little c times norm of the input. And if you rearrange this into input less than or equal to 1 over c times output, you can see that this here is giving you a bound on the norm of the inverse operator, where you are exchanging the roles of input and output, right? So the output of your inverse is less than or equal to this constant times the input of your inverse. So this shows that your inverse has norm less than or equal to this 1 over c. And this is exactly what we need now. So we apply this to our operators on the subspaces xn. And from these two things you get stability of your sequence. And for Polsky, all we need is now invertibility of A, but we get that by lemma 9b from the positive definiteness of A. Okay, now finally Polsky's theorem comes in, and we get the applicability that we claimed. Okay, proof is over. So let's take a little break to celebrate the achievement. Theorem 10. Remember when we first studied projection methods, or even more generally when we first studied approximation methods, where we only had strong convergence of the operator? Then the answer was, well, sometimes it works, sometimes it doesn't, you never know. And we said, yes, we need theorems that tell us, for this class the answer is yes, for other classes we don't know. Now here's the first theorem in this direction, because this is a positive answer for a certain class of operators, which are the positive definite operators. And the class of approximation methods that is covered is, well, it at least contains the finite section method and therefore all versions of Galerkin's method.